Yeah, when I left Zoom, everyone got kicked off too. So everyone's just joining in again.
Audio. Right. Can you guys hear me okay? All right. Great. Okay, continuing on. All right, great. Okay, take it back to the room. Thank you for answering the question. So in Python, we know that we can create a list using that nice first class syntax. And in the last lecture, we saw how we could do the same thing in Java. Unlike Python, it's not a built-in type in the same way. Instead, it's a utility type that's added to the language. And so what we're going to do today is learn how to write our own list from scratch. And in particular, we're going to be taking advantage of the idea of recursion. And it'll build really nicely on what you saw in 61A, or if you didn't take 61A, just the idea of recursion in general. It's really nice, this idea of recursion and recursive data structures. It'll allow us to build data lists that can extend infinitely. Okay. Uh, so the first thing we need to do before we get to this process is we need to solve something called the mystery of the walrus. That's just my name for it. And it'll give us a strong foundation upon which we can build lists. So I'm going to start here with a question you are not equipped to answer, in which I have an object called a walrus that has two properties. I have another variable, walrus b. I say b equals a, and then b dot weight equals 5. So the question is, does that change propagate? Is it the case that both walruses are affected? You can use this QR code or yelkey.com/true. And then I'll do the second question. So I'll give you a minute to answer that. And I have not told you how to answer this question. You must use your intuition. I went turn.
I get the mic.
Oh, yeah. We have problems.
Just like,
Oh, let me.
okay. Just say, if you're just coming in, no, you can't see it in the always. Okay, good. All right. Hey, if you just came in, as a reminder, we cannot let anyone sit in the aisleways. Can you raise your hand if you're right next to an empty seat again?
Yeah, here.
Yeah, there's one back here.
We got like 5. Higher.
Raise your hand higher.
There you go. Great. Thank you.
All right.
All right, next question. I'm not going to tell you the answer to that. Oh, wait, I am going to tell you now. First change does propagate, and I'll show you that visually in a moment. So the first one does propagate. How about the second piece of code? Does this change propagate? Sorry if this QR code's interfering. Oh, it's saying, oh, sorry. Let me fix that. Don't request X. Publish. Okay. It'll work in 1 sec. There you go. Should work now. Okay, interestingly, so the first time you guys were split, this time you guys are mostly saying no, it won't propagate, and that's correct. It will not propagate. Okay. So the propagation does not happen in the second case. As a way to so again, I haven't told you why this is why it's the mystery of the walrus. We don't know how to answer this yet, but I'm going to give you a little preview of why this happens with the visualizer here, this Java visualizer. So if I run this code, the visual picture we're going to work our way towards is as follows. I'm going to scan this thing forwards, and I'm going to show you that when the code is running, this is basically the situation. When I say A equals B, they're pointing at the same walrus. But when it comes to the integers, they're not the same. These are two separate little boxes. So this is the picture we're going to try and build in our mind painstakingly. And that's going to be the answer shortly. Okay. All right. So I don't expect you to be able to answer it well, but that's where we're going to begin our journey. So we'll start by talking about bits. Your computer has to store whatever information it has in memory. And our model in this class, and a good model of what's happening in hardware, is that the information is stored as a sequence of ones and zeros somewhere. So for example, the number 72 is stored often as 0100, 1000. 205.75 is stored as this sequence of numbers, and there's more at the top end that I'm not showing. You'll talk about that in 61C. The letter H is usually stored as 0100, 1000, which you'll notice the same as the number 72. True is often stored as 7 zeros, then a 1. And what happens when the Java programming language is manipulating memory is that when it sees the bits, it has different ways of interpreting them. So in Java, when we declare a type like int x or double x or float x, these are what I'm calling here the primitive types. The only two that we've really seen so far are int and double. And there's 6 more we aren't really going to talk about much in class. But what Java does is, given the type, it will interpret the bits in memory in a different way. Now, 61C talks about like, why is 205.75 this? Totally beyond the scope of our class. That's their class. Okay? But the point that you should care about, and I'll take the question in just a sec, is that Java thinks about the chunks of bits in terms of the types that the variable is declared as. Go ahead, question. Big Indian, little Indian stuff is 61C. Yeah. Yeah. So right here, I note that precise representations vary from machine to machine. A lot of hubbub around Indian. That's surprising. Right. Okay, declaring a variable. So I'm going to give you my model that is not totally exactly how Java behaves. But when you declare a variable in Java, a good mental model is that this is what happens. Your computer sets aside a number of bits that is exactly enough to hold that type. So for example, integers are a box of 32 bits, and doubles are a box of 64 bits. So you get a box that can hold those bits. And then Java has some kind of internal table that says like, okay, the variable name X goes to these bits, the variable name Y goes with these bits, okay? Now, when you first declare a variable, Java doesn't put anything in those boxes. It's not like it fills it up with zeros. It's just some stuff. But Java won't let you print out a variable that is uninitialized or use it in any way. So you can think about it as follows. When I say int X, we get a block of 32 bits in a row that stores X. When I declare Y, I get 64 bits in a row. It has something in it, we don't know what, and we can't see it. Once we say X equals negative whatever, I get this sequence of bits, and that's because at some point somebody decided this is how we should represent that number. But this number right here, that's that negative billion number. Likewise, when I say Y equals this, I get this sequence of bits. And again, the precise mapping, like why the sequence of bits is this number, that's 61C stuff. We don't care about it. Okay? You just know that it is some sequence of bits. All right. The real picture is more complicated. There's stuff about like registers versus memory, all that. And again, it's all 61C. So this is a bit of a simplification of how computers work, but it is close enough to reality. Now, I find it annoying to look at these boxes with bits in them. They're hard to interpret. So I'm going to make up something all called simplified box notation. And so instead of writing the contents of the box in binary, which is what really is happening, I'm going to write them just in the human readable symbol. So when I say X block here, this is really 32 bits. It's just that I'm interpreting it for you so you don't have to think about what it means. Okay. All right. So with this in mind, I can tell you what the equal sign does. This is something called the golden rule of equals. I made this up. Given variables Y and X, if I say y equals x, what the equal sign does is it copies the bits. So whatever the 32 bits are, 64 bits are, 8 bits, they just get copied from one box to the other. So the example I had from earlier, when I'm running this code, if we look at this, so when I get to, when I say x right here, this is a box containing, let's see, let me zoom in here. How many bits is this? 32, great. And when I say y equals x, it takes those 32 bits and does what? Copies them. Great, that's the golden rule of equals. So whenever I say x equals 2, right here, I'm going to take the bits over here, which is whatever the bits are for the number 2, and I'm going to fill in this box. Okay. All right. And we'll come back to the walruses. Right, any questions? Other than why were they pointing at the same object? Yeah. That was your question. Great. Okay, well, we're going to get right there. Okay. So I mentioned earlier that Java, that there's these 8 primitive types that are some fixed number of bits. Everything else in Java that's not one of those 8 types is a so-called reference type. Okay? Reference types behave a little differently. So when we instantiate an object like a dog or a walrus or a project from the old Spring 19-ish Project Zero, what Java does is it creates a box of bits for each instance variable, right? That makes sense. So a walrus has a weight and a tusk size. So it's going to set aside 32 bits for the weight, 64 bits for the tusk size. And then when you instantiate an object, it does get filled with a default value. That's not super interesting. Like I said earlier, if you declare a variable, there's no default value. When you instantiate an object, there is a default value, which is 0. And then the constructor will often fill in the boxes with some value. Okay, so let's see a little demo here. These aren't the most thrilling demos, but I think they're nice. So when this code is running, I'm going to say, let's create a new walrus. So we step in and we get 2 boxes. We have one box that's how many bits? Not 0 bits, 32 bits. 0 bits would not be useful. And then we get another box, which is 64. And that's just because earlier I said doubles are 64. All right. And they get filled in with a default of 0. And as it turns out, the thing I invented called simplified box notation is the number that shows up in this visualizer. Now the constructor goes in and it says, I'm going to take what's in this box. So there's this W box. It's called W. It has 32 bits. And it takes this 1,000 and it copies the bits over. Okay, so look, we just copied those bits over. And likewise for the tusk size. Okay, so that's the golden rule of equals. All right. Then you'll notice in the visualizer, there's this interesting thing that happens here, which is that I have a box called A with an arrow, which is pointing at an object. That's what we're going to talk about now. Okay. So here's my 32 bits for weight and tusk size. And now let's talk about what happens when you actually create an object. So here is memory. You can think of memory as a linear sequence of bits, just a whole lot of them. Maybe it's, several gigabits of memory. And somewhere in memory, we have our weight, which is the bits in green. And then we have these 64 bits in blue, which are the tusk size. And in reality, there's actually a little more information. There's some header information. So an actual object is a bit more than 96 bits for a walrus, but we don't care so much. And this is where it lives in memory. Okay. And so what Java does when it creates an object is that the new keyword, you can think of it as it finds a place in memory, makes the walrus, and then it says, I'm the new keyword, and the walrus I just created got put in position, let me count these out, 2.384 billion, right? This is the memory bit number where it put the walrus. Now, in practice, this isn't going to be on an exact odd numbered bit, and in practice, there's actually this whole stack of ideas like virtual memory. Again, that's 61C, but this is pretty close to reality. And so if the object happens to be created in memory location 2.384 billion, then the new keyword returns that number. It says that's where I put it. Okay? You can think of that's what new does. It makes the walrus, and then the return value of new is the address of the walrus. All right. It's a little bit more to the story. And then I'll take questions, right? Actually, any questions about this so far? Yeah? No, there's no ampersandy stuff in Java. Yeah. There's a lot of new things happening with the type system. Maybe in 2 years it'll be done, but not now. Some project called Project Valhalla that tries to unify things a little more. Yeah. Is the Kotlin better than Java in every way? This is beyond the scope of our class. Kotlin is a nicer Java in many ways, though. I think that's fair to say. But Java eats the good features of Kotlin over time. Yeah.
You please repeat what new does?
So new does two things. One, it goes to memory and it finds a place for the walrus to live, because you can't use bits that are already used to, like, for your picture of your face or whatever. So it finds a place for the walrus. It puts the walrus bits there, and then it keeps in mind, where did I put it? Oh, I put it in position 2.3 billion. So it creates the object and then it records its location. Yeah. Is there a limit to the size an object can be? Probably, but I have no idea what it is. Yeah. Yeah. Well, Java might have a language restriction though. Yeah. I don't want to talk about stack or heap memory today. Sorry. Yeah. All right. Proceeding a bit. So when we declare a variable of a reference type, so there's 8 primitive types, int, double, all the rest, and anything else, a string, a dog, a planet, an object, a list, anything else, those variables are 64 bits. And those bits are the address. By default, it's null, which means nothing. There is no actual object. But the other thing it could be is the address of a specific instance of that class. So it's this number right here, 2.3 billion. So what goes in the box is the address. Okay. That's a different, some languages could have done it the other way. You could have designed the programming language so that what goes in the box is the entire walrus or the entire list or whatever else. But what Java did is they put the address of that object. Okay. That's what they decided to do. And so, for example, when I say walrus, sum walrus, if I say equals null, I get 64 bits in which I put all zeros. If I say equals new walrus, I get whatever address the new keyword shouted out, right? So when we created this walrus, it shouted out the number 2.38 billion. That's where the walrus is. We took those bits and we put them in the sum walrus box, because the golden rule of equals is copy the bits. So if the bits on the right-hand side were an address, that's what goes in the box. Okay. Yeah. Sorry, one sec. Yeah, we're not going to do any fancy AVR type stuff. No. Yeah.
Wait, so the address and the reference based on address or location of the object.
Yes, the address is the location of the object in memory. Exactly. Yeah.
Well, I guess like it would take a part, like it would take a sector of the memory. Then does the address point to like a start, a finish, or
the address points to the start of the object. Yeah. Whatever the first bit is. So this green bit here. Yeah. Yeah.
no assignment. Memory still be good.
If there's no assignment, what happens? So what'll happen is these bits will get put in memory for the new walrus. And then there's something called the Java garbage collector that realizes, oh, nobody's actually using this object, and it'll free it and mark it as usable memory again. Yeah. Yeah.
How many bits are set aside for null?
If you set aside a null, it's 64 bits, just like usual. Yeah. So because this box, it always has 64 bits. The default is it's 64 zeros. Yeah. Yes, this is the memory address. This is nothing. And this is, yeah, this is the exact memory address. Yeah. So if you have an integer, it's 32 bits that correspond to however you represent an integer. So for example, the number 72 would be 24 zeros and then those 8 digits I showed earlier for 72. It would be the binary representation of 72. So with an int, it's not an address. With a char, not an address, double, not an address. It's literally the raw thing itself. All right. Yes. The 64 bits that we show on this page are not very useful. So what we're going to do instead is any address that is all zeros, we're going to write it as null, like this. And then if it's a non-zero address, we're going to represent it as an arrow, because we don't know the contents of memory, nor can we read the sequence of bits. So I'm going to use this arrow to mean these 64 bits in this box are pointed to this address. Okay. But really what's happening is there's 64 bits here, which are where this walrus lives. And that arrow is the visual representation of that fact. All right. So in terms of our visual metaphor, let's talk about the golden rule of equals again, but now with this metaphor in mind. When I say walrus A, I get a box and it's how many bits? It's on the screen, but 64 bits, and it's some default value. It's not zeros. It's just, we don't know it's there. When we say A equals new walrus, a walrus gets created. And what does new return? The memory address of the walrus. So where do those 64 bits do? They get put in this box, and there it goes. Okay. When I say walrus B, I get 64 more bits. And then when I say B equals A, what happens? We copy these 64 bits here. Okay, so they both have the same address, is another way of putting it. So they're pointing at the same object because we copied the same address. Happy? Okay, so that's why the change did propagate before, because when we said B equals A, we're pointing to the same object. Why might you do it this way? Like, what's one advantage of just copying the address instead of copying the whole object over, which is another way to design a programming language? Yeah? Say again? It's quicker, right? So imagine that you have like an object that's gigantic, like a list of 1,000,000 numbers. If you say B equals A, you're just getting a reference, and you just copy just those 64 bits instead of having to make a copy of all 1,000,000 integers or whatever. Okay. All right, let's talk about parameter passing briefly. So let's suppose that we would like to pass values to a function. I want to point out that parameter passing uses the same golden rule of equals. So if I have two variables B and A, as I said before, the golden rule of equals, when we say B equals A, all we're doing is copying the bits from the right-hand side to the left-hand side. Passing parameters is the same exact thing. Okay, so let's try that out real quick. Here's the main method. That's where we're going to start. When I say double x equals 5.5, I have 64 bits. Okay. Then I say y equals 10.5, I get 64 more bits. And now when I say the average is the result of computing the average, we go to this function, and these two things are a new variable declaration. So we're going to get a new variable A, which is how many bits? 64 bits, and a new variable, which is 64 bits. And then we're just going to copy the bits over. Okay, so since these are just copying the bits over, they're not a reference. Remember, what goes in a primitive value or primitive variable is the raw number itself. There's no address. So we're just making a copy of 5.5 or 10.5. Okay. So passing items into a function is just copying the bits like before. Okay. Because we're just copying the bits, Java is a pass by value language. In fact, you can only pass by value in Java. Okay. It does so happen that sometimes those values are addresses, but there's nothing like in C++. Someone asked about the ampersand thing. You cannot pass by reference in Java. You can only pass by value. It's just that some of the values are addresses. Okay. All right. So to summarize, there's 9 types of variables in Java. We have these 8 primitive types, and for those 8 primitive types, the boxes contain literally the raw value. The 9th type is any reference to an object. That's why they're called reference types, and references can be null. When we use this box and pointer notation, each variable is a labeled box of some specific size. So these are 64. And the values are shown in the box. Now, for the values which happen to be addresses, we're going to show them as arrows pointing to objects instances. A little bit torturous of a metaphor, but it works. And the golden rule always is that when we do B equals A, we copy the bits. And we pass parameters, we copy the bits. That's the whole story. So now I'm going to see if that all really made sense and give you a minute or two to think about the mystery of the walrus again. So now I have a function called doStuff. Actually, I'm going to walk you through the code. So I create a new walrus. I set x equal to 9. I pass the walrus and x to this function. It does some stuff, and then we print them out. So I want you to tell me which thing you think happens, and then I'll spoil it in about a minute. yellkey.com/involve, or take this screenshot. And if it's not working because I didn't set it properly, I'll fix it. I see answers coming in. The questions are not points. They're fun. It also lets me see how you guys are doing. Are you happy with that? How's chat doing? Yeah, there's more people that know. I haven't looked at the survey this time around to see how if it's. I seem like more people know Java than usual, which is usually 50%. We should check. All right. Let's check it out in this visualizer, even if you haven't answered yet. Okay, here we go. I'm going to skip forward a bit to the part where we have created the objects. Okay, so the setup, make this a little bigger, but not too big. The setup is we're about to call do stuff. When we do that, we'll have two new variables. What will this variable, how many bits will it be? 64, I agree, not 96, it'll be 64. And this one will be 32. And what do? We copy the bits. So these 64 bits will get copied so that the frame, when this function comes to exist, do stuff, its W variable is pointing at the same object. So the W change will propagate because it's pointing at the same object. We copied the 64 bits. So that there's only one walrus, in other words. Okay, it's like that, the Matrix movie. There's only one walrus. 3,400. When we say x equals x minus 5, here we have our own local x. And so the change will not propagate. Okay, so the answer is when we print it, we get 3,409. Okay, if you didn't get that yet, that's fine, but you should know it by the time of the midterm. And this is the fundamental underpinning that will make our lists work. Question. What if we use a wrapper class for an integer? We could construct an integer class that would allow the change to propagate. If we're talking about the capital I integer class, it would not propagate because they're immutable. And that's nothing that you guys have learned. So that's just someone knew something about Java you didn't. Okay. Yeah, next question. Okay, so the visualization link is there for you to play with more, and I'll take one more then, yeah. Sorry, everybody, I got to hear this question. Yeah, go ahead. The name doesn't matter. Yeah, so the fact that I happen to name it X as well is irrelevant, if that was the question. But there's a little bit of buzz. I'm going to proceed just because it's like a little too much excitement around the question. All right, I got one more thing I want to teach you about that's foundational, just to review some of the ideas we've had from the last lecture and in this one, and then we'll do some cool recursive programming. Okay, so arrays are also objects. And as we've seen, objects are usually instantiated using the new keyword. So I'll usually say new dog, new whatever else. If I declare an array, declaration, what it does is it creates a 64-bit box, if it's an array, that's for storing a reference to an int array. But when I do this, there's no array actually created. This just makes a box that can store the address of an array. It's only when I actually instantiate the array that I can actually get an array. Now, I have a tiny note that you usually wouldn't say instantiate for an array, but I'm going to anyway. But if I say new int bracket 0129554, it's one way to make an array. This makes a new object, which is an int array. And that object I'm saying is anonymous because we haven't put it anywhere. Okay. So there's this array. Okay, it has 5 boxes. They have integers. This is a line of code which declares, instantiates, and assigns the address. So this creates a 64-bit box for storing an int array address. That's right here. It then instantiates this array, and then it copies the 64-bit address into this box. Now, instantiated objects, as I've alluded to, can be lost. Like if I reassign A to something else, like I pointed at an array that's 345, this array still exists somewhere in memory, but there's no variables pointing at it. And if I do that, eventually the garbage collector will come and consume it. It's a little beyond the scope of our class. We'll say a tiny bit later. Okay. Now, there's another little point I want to raise, which is that the equals operator is the cousin of the equals operator. When you say are two things equals, you're just asking, are the bits in box X the same as the bits in box Y? Equals a literal bit comparison. So if I have two arrays X and Y that happen to contain the same information, equals will say false because the bits in this box aren't the bits in this box. If you want to actually compare these two arrays, you have to use something smarter. For example, you can use arrays.equals. So arrays.equals will say that these two X's and Y's are equal. And an example of an equals that will compare two things and get back true are these, right? So Z and Y are the same object, so we get back true. Right, so equals is basically the same as equals. Arrays are another type of object. All right, so a lot to digest here. And that's what discussion worksheets are for, and that's what getting ready for the midterm is for. So I hope this is a good foundation, but I do want to switch gears a little bit and not get bogged down too much of this. And I want to talk about how we can now build a list using these ideas. Okay? So what I'm going to do is I'm going to create an infinitely extensible list using this basic idea, and I'm going to do so by creating a new file, which I will call int list. Hopefully it's okay. I got to make a new package. One sec. Okay, so this is the lecture code repo. It has packages. Oh, there's already a package called int list. Okay, hold on a sec. I got an idea. All right, I'm going to undelete my file, and then I'm going to delete its contents. Don't look at it. Okay. So here, let's make this slightly bigger. I'm going to make a class called an int list, and this is an infinitely long list of integers. That's what it's going to represent. I'll just say an infinitely long list of integers. That's what the class is. And it's going to have two variables. Why are you yelling at me? Oh, because it's not .java. Star. Extra star. Oh, package statement. Oh, thank you. I'll fix the star. Package lect3 intro. And don't worry too much about what that thing means. Okay. All right, you want one star? I actually don't remember the convention. I haven't been writing Java code lately. Okay, I'm going to have two things. I'm going to have the first number in the list. I'm going to have the rest of the numbers in the rest. First number in the list. This might feel a little familiar from 61A. And then I'm going to have a main method and start using this list. So this is the whole thing. I've made an infinitely extensible list. It's not a very good infinitely extensible list, but it works. So I can, for example, say int list equals new, int list L equals new int list, L dot first equals 5. And I'll say L dot rest equals null. I don't actually have to do that, but I have. I'll do the visualization in a second. There are linked lists in Java, but we're building our own. You're right. Okay. So the whole goal is to show how we could build our own. I'm going to add another number to my list. The syntax is weird, but it works. Just being very explicit here. Okay, and then I'm going to say L.rest.rest equals new int list. And I'm going to show you this visually in a second if you're feeling uncomfortable with it. Oops, I messed up. L.rest.first equals 15. L.rest.rest.rest equals null, I guess. Okay, let's look at this thing in the visualizer and see what it is we've built. Okay, we have a problem. Oh, that's because that's a different file. We're just going to delete this for now. Okay, so here is my visualization. When I say int list L equals new int list, oh, you're so small. That's sad. Okay, I guess I should have tested on the screen. Why so small? Hold on. Oh, there it goes. It's bigger now. Good. Okay. All right. When I say L equals new int list, I get a data type that has two variables, first and rest. How many bits is this one? 32, and this one is 64. This is the first number in the list. When I say L.rest equals new int list, what's it going to put in this box? A pointer to another int list. There it is. Its default value is 0 and null. We set that number to 10. We set that to null. I'll notice I don't actually need to do that, right? It's like redundant. That's null by default. Okay, I step through again, and now I get a list. Uh-oh, I messed up my code. Someone spotted that earlier. Okay, now I understand the murmuring I was hearing. Let's visualize again. And let me get rid of the nulls, actually, or this time. So hopefully you all agree that this is a list of numbers, even if the syntax is annoying. Okay, so L.rest equals new int list. There it is. L.rest.first equals 10. L.rest dot rest. What am I going to put in this? Pointer to a new int list. And then I'm going to say it's 50. So in principle, you could use this technique. It'd be a very awkward programming environment to work in. I would hate it, but it would technically work. I mean, it's not really scalable because of this feature. Like, it just seems awkward to work with, but it's a start. I'm going to make things a little nicer. And then I'll take questions after I do this part. I'm going to add a constructor to the int list so that I can just pass arguments to it like we did before. Okay, first equals f, rest equals r. And if I did this, the code would look something like this. L.rest equals new int list null. L.rest equals new int list 15 null. Okay, so that would work, but I'm actually going to show you an even cooler thing you can do since this is recursive, which is I'm going to go the other way. So that will work fine, but I'm going to go the other way, and I'm going to say int list L equals new int list 15 null. Then I'm going to say L equals new int list 10 null. No, not null, L. And then I'm going to say L equals new int list 5 null. L, jeez. Okay. So how do I think about this? I really trust recursion. I'm saying I'm making a new list that has the number what in it? 15. Okay, great. Then I'm going to here make a new list, which has 10 as its first number. And what's the rest of the list? 15. 15 null, sure. Okay, and then we make a new list, which is 5 at the front, and then what? 10, and then 15, and then null. And so if we run this code, and this is why it's important you have taken 61A and you understand recursion, because we're going straight into this stuff. If I think about what this code does, first I get 15 null. Then I say, L, you're not going to be this list anymore. You're going to be a list which has 10 at the front. And this address is going to be the rest value. Okay, so there, we got 10 and then rest points at what we used to have. Then we have a new one, which is 5, and then rest points at this. Project 1A is going to be you working to the nth degree with this notion. So it feels a little fuzzy. One thing you can do is get the repo, the lecture code repo, and step through. Okay, I didn't actually step through the individual steps. I was stepping over. And the other is, of course, when you do Project 1A, you'll be doing this in great detail. Okay, so any questions about this so far? Okay. Yeah. At the end, L is pointing at the front of the list, the 5. Yeah, so it has the 64-bit address of this right here, the 5. Yeah, and it's pointing at the whole box, the whole node, the whole int list. Okay. All right. The next thing I want to do is write a size method. Again, this is nice recursive code. So we're going to have public int size, and this is going to return the number of items in the list. So I'm going to do a little recursion demo in the room. And I'm going to go to you. I'm going to ask you a row unit. A row unit. Yeah, you're cheating. So you guys don't know. I'm going to ask them about that. So you're not sure room unit. I'm going to be recursive. Yeah. Oh, no, you're still cheating. You guys know this. Okay. What row unit? Okay. Okay. You don't need to go in Here's row 1. Here you go. Here's 6. Okay. And then row 2. And you keep going. So the basics. So we're going to do that. Okay. So I'm going to say, if the rest is null, that's you in the front. You say, Professor, what row am I in? It's 1. Okay, good. Otherwise, you're going to return 1 plus rest.size. That's going to be the idea. And if I stop the code and I system.out.println L.size, I should hopefully get 3 if I didn't mess something up. Okay, we get 3. Good. All right, good. So that's the recursive approach. I'm not going to step through it in code because I actually find it more confusing, personally, to step through recursive code like this. More about understanding. I mean, you're welcome to, but I find that in lecture, it's very confusing to watch. Okay, so that's one way to do size. Any questions about this? Yeah.
This doesn't work in Python, right? realized, remember I tried to do this in Python, it didn't work.
You can write code that will work like this in Python. I don't know. It depends on where you start, but I'm gonna table that question for now. Yeah, it should work fine if you set it up matching this, but you may have been doing something slightly different. You can ask me after. Let's also see how we can write this code iteratively. Get the size of the list with iteration. I'm showing you this because often we want to see both the recursive and the iterative, in an educational setting, see both of the ways of doing things. And what I will observe is that I don't like this nearly as much. That's just me. So if I want to get the size iteratively, one thing I can do is I can say p, I'm going to make a new variable p, and I'm going to point it at myself. Okay. And then what I'm going to do is, as long as p is not equal to null, I'm going to add total size plus equals 1. It's yelling at me. You've got an infinite loop here. Okay, well, I need to say p equals p dot next rest. And then I'll return total size. I think this works, assuming I didn't mess up my code. This one I will step through. So we should get 3 again. Iterative size. Okay, what do we get? 3 again. Great. Okay. This one I'm going to step through so we can see what's happening. So in the iterative version, okay, let me move this panel out of the way. In the iterative version, when this code's running, the iterative size method, it has implicitly the variable this. It's pointing at myself. I'm going to say total size equals 0. Then I'm going to create a new variable p, which is how many bits? 64. And what's it going to get? Myself, my own address, an arrow that points at myself. And then as long as p is not null, I'm going to add 1 to the size and then advance p. Yeah, sorry that the visualizer's behaving a little funky right now. I think it's the HDMI cable somehow. Okay, and then p becomes null eventually. So that's another way to write size. I don't like it as much, but maybe you like it more because it's less mysterious and recursive. Any questions about this? Yeah. How did I pass the instance I'm working with? Right here, I told L, hey, list, the list that is 5, then 10, then 15. Actually, I'll stop it right there. Let me run it again. When I'm about to call this line of code, I'm asking L to do the work. So then L is going to be thinking in terms of itself, this. We could put an argument in the method. Yeah, we could do like static int list or something. And then I would just do, like, that would work too. You have to call it differently, but it would work. Yeah. Why is the recursive case? I didn't use this. I could have. I could say this.rest.size. That would have been fine. Yeah. You might even argue that's better style. I don't know. Other question. Yeah.
Say it's equal to this, and then this share the same with memory 64 would that also advance this?
It doesn't advance the this. That's a good question. The question is that going to change this? And let me show you why. We'll go right to that line of code. This is a great question. So when you have this question, the way to think about it is think very carefully about what happens. So how many different memory boxes are going to be affected? Just one. Because it's P. This is the only memory box that gets changed, right? So when we say P equals P dot rest, it's only changing these 64 bits and not this box. Does that make sense? Yeah. Other questions about that? Yeah. Anytime you call a function that's any non-static method, it will create at least the visualizer displays it as this gets created with your own address. Internally, probably not. All right. I have a question for you now, which is I want you to think about for a minute before you go. And am I going to tell you how to do it? Yes, I'm going to. If you are someone really itching to get out of here for whatever reason, you can leave. But I'm going to give an answer to this question. So for 2 minutes, I want people to think about how you might implement a method called get that gets the ith element of a list. And if you're watching the webcast, you should pause and actually think about it. So think about this for a couple of minutes and I'll spoil it for you. I'm taking back the room in 22 seconds, so. Or am I? All right, hi folks. Okay, if you did not successfully leave, I'd love for you to chill for a sec, unless you're awkwardly blocking a bunch of people. I don't know. All right. Okay, ready? Let's talk about how to write this thing. Okay. So I'm going to write a method public int get int I. And it's supposed to get the ith element of the list. So I'm going to try and do it recursively. What feels like the base case to you? If I is 0, what should we do? This dot first. You could also just say first. Otherwise, what should we do? 1 plus? No. That rest dot get I minus 1. That sounds pretty good to me. Let's see if it works. Let's try doing system.println get 1. Okay, so if this works correctly, we should get 10. We'll see if the students are correct. Okay, we got 10. Hooray, good job, guys. What happens if I do 100? For you, good. 100. You got an error. Null pointer exception. All right, all right. Okay. So there's more practice. If you like these little recursive problems, there's some in the lecture code repo you can play around with that I just added again. I'll see you guys later. Feel free to come up with questions for me or my children.
I was doing
Yeah.
homework 0A.
Yeah.
And on the on IntelliJ, I was writing a test. Right, I passed all the tests on the Java board I submitted to grade school. I failed to the test.
Oh, you passed them locally, failed them remotely?
Yeah.
This is a question for Ed. It shouldn't happen.
Well, I mean,
yeah.
I fixed it. Like I was able to fix it and submit it. But
oh, my hair.
but